Hello, everybody. Welcome to the ocean observation track on the effective use of sensors. We've got three really interesting talks to go through, and hopefully we will have a discussion session at the end, and there will be technical questions after each of the presentations. So first up is Damien Mallard from NKE, who's going to talk to us about a really interesting technique using refractive index as a direct measurement of density and salinity. So Damien, please load your slides, and really looking forward to your talk.
Thank you, Matthew. So first of all, for those of you you don't know me, so my name is Damien Mallard from NKE Instrumentation. I'm a research engineer, specialist in metrology, optics, and physical oceanography in the development office of NKE Instrumentation. So I'm also a project leader in European National Research and Development Project. So our company is a specialist in instrumentation for oceanography. We manufacture floats for Argo program and drifting buoys. We develop and manufacture multi-parameter probes and sensors, and also automate networks. So let me introduce quickly the team who works with me. So we have Arnaud David, our CTO, Chief Technology Officer, and Yves Degré, our Managing Director. So as you can see on my screen, my topics today is the last result before COVID crisis on the nose sensor. So towards in situ absolute salinity measurement and new profiling float observation in the northwestern Mediterranean. So my talk is particularly relevant to those of you who are operational oceanographer, scientists, meteorologists, and my presentation will last about 20 minutes. And by the end of my talk, I hope you will be familiar with the nose sensor. So please, the summary of my presentation. So I've divided my presentation in 4 parts. A brief introduction. Next, I will start by present the performance of nose sensor, the correlation between nose sensor and absolute salinity, and discussing how to determine absolute salinity with this sensor. And then I will move on the result of several demonstration results on float and part on scarosity performed with the nose sensor. So the objective of the demonstration, so I will show you what our nose sensor can bring to the community of oceanographers, in addition to current or existing sensor. And I will end with some action conclusion for improving the performance of nose sensor in marine environment. So what is the theoretical basis? So just remind some information on the nose sensor. I explain you the performance of the nose sensor and the principle of the nose sensor. So the nose sensor is a high resolution in situ refractometer. So we use a property of laser light in seawater. So of course, if the salinity of your water change, your refractive index change, and we associate temperature and pressure measurement on the algorithm, because refractive index is dependent on temperature and pressure. So this sensor has the particularity to have accuracy in refractive index better than 10 to the -6. An absolute salinity determined after calculation 0.005 gram per kilogram, and after calibration in laboratory density, an accuracy of density 0.003 kilogram per meter cube. So you have a picture here on the nose sensor. We have and the parts of detection is here. So your laser beam will propagate in the medium, and after variation of salinity, your beam change its direction. So we measure the very high precisely. We measure the deviation of the laser beam with a position sensitive device. So to obtain a very robust sensor, we qualified the node sensor over the last year in different areas. So we qualify and validate the nodes in laboratory to, for example, to improve the algorithm of composition to the effect in temperature and pressure in the refractive index. We evaluate the node sensor on both at pressure atmospheric at pressure atmospheric pressure, sorry, and some result has been expected in the Santon cruise. This campaign will be last 6 months, and after that we qualify the node sensor on CTD carousel during different cruises, PSH and NOPS, and we deployed in 2009 the sensor on profiling floats. So now, how we measure, how is the salinity defined? So of course, if you take a volume of seawater, you have 26.5% of water, and salt represent 3.5% on this volume. So the sea salt is composed by chloride, sulfate, sodium, magnesium, calcium, potassium, sorry, and mineral constituent represent 0.7%. So since 1978, the measure salinity is practical salinity, but the salinity relevant for thermodynamically describing seawater is absolute salinity. However, this parameter has been accepted and used since 2010, but the problem as no instrument can currently measure it operationally. So in the ocean hydrological database, we found practical salinity, and this parameter is measured using conductivity that we have only, it's only unique part of dissolved material which is measured. In publication of Miller in 2008, a new term appear. It's a reference composition salinity. It's a best estimate of composition of standard seawater North Atlantic, and is derived from practical salinity. So we have a relation between SR and SP. Absolute salinity is the mass fraction of dissolved material, so it is related to the density of seawater, and reference salinity is defined by this equation with the term SR, and composition anomaly, delta SA, is dependent on longitude, latitude, and pressure. So this term is the composition anomaly due to nutrients and other minor components. So this term has been defined by McDougall and Wright in their publication 2012 and 2011. So the absolute salinity is also a biogeochemical parameter. It is dependent not only on dilution, but also biological pump. However, in the thermodynamic equation of state in 2010 and McDougall in 2012, so the composition anomalies released on very limited historical silicate measurement to fit with density sampling. So we have a here contained. So it's a map of silicate at 100 decibel, and the composition, composition anomaly at the same pressure depth. Now I will show you an overview of the link between refractive index and absolute salinity, and refractive index and density. So the link between the density and refractive index, so the node sensor, it's operated by laboratory calibration. And if we want to compare the house sensors with existing sensors, we we have a relation between the absolute, we determine absolute salinity, and we have a relation between reflective index and absolute salinity identified by Stever-Miller algorithm. So now I will show you some results of a different demonstration of the nose sensor on a large generation of profiling drifting floats in the Mediterranean Sea. So we, in 2019, so we configured a mission of the node sensor mounted on profiling float, and we configure the mission as follows: one profile per day on 15 days, and then one profile every second day. So the objective of this cruises was to identify the effect of biofilling on the measurement, and to qualify and provide a maximum of profile in salinity with the nose sensor. So we acquire salinity with the nose sensor, and we compare this salinity with SB41 as a function of SP, and we measure, we calculate SR, and we compare the SR determined by the SB41 and the nose sensor. We measure, we achieve also temperature, pressure, and reflective index profile. So look here, so we collect 50 profiles. So I just here represent 30 salinity time series with the nose sensor. So we have on the graph here the salinity, practical salinity plotted in a red line. We plot the salinity of the nose in the blue line and the reference salinity in black line. So we have 30 profile represent on this graph. So between 0 and 1,600 decibel. So what we can conclude on this result. So we in the from subsurface to the photic zone. So we measure difference as nose less SR up to 0.1 gram per kilogram in this layer, and we have we identified this difference by a possible biological activities between 400 and 1,200 decibel. We overestimate the nose sensor, the nose salinity compared to reference salinity up to 0.025 gram per kilogram. So we need to confirm this this difference between the nose sensor and the reference salinity with new version of nose sensor optimized, ideally in the same area. In the deep zone, so we measure composition anomalies less 0.01 gram per kilogram. So we have a good agreement of nose salinity with the presence of salinity anomalies in the Mediterranean Sea. In temperature, so I just we plot this 30 profiles in temperature. So we have a very good shape and very good behavior in temperature between the two sensors. And I just make a comment about Tara team. I would like to thank them that they recover the float in the Mediterranean Sea on extreme meteorological conditions. I would like to thank them because the float drift a lot, and we call them to recover this float. So how we can say on the prover nose float and this mission. So it's a first successful long mission of the nose sensor on profiling float. So the items focused by the mission on float are present on this table. So we have very good results. We acquire all data file, and all transmission has been realized. We have a good navigation and behavior of the floats. We conclude by a very good plug-and-play architecture for profiling float integration with the node sensor. And we validate the behavior of the node sensor on this float because no fouling has been hasn't been appeared on the cell of the node sensor. The only bad point concerns the sampling frequency. So we need to increase. We would like to increase the sampling frequency of the node sensor compared to the existing sensor. So we plan new increases in 2021. We hope that it's possible, depending on the COVID crisis. And during the new crisis, we review mechanical design and reduce the background light. And of course, we will optimize the mission of floats. And second point concerns the post-processing analysis. Some confidential information about another crisis that we performed with the node sensor. So it was in 2019 with a team coordinated by Simon Tiwis. So we deployed the node sensor on carousel CTD in Baltic Sea. So during this crisis cruises, we obtained 16 profiles, so 32 time series of salinity nodes, temperature, pressure, reference salinity with the SB9, and this profile would be up to was up to 40 met depth, and we characterize the node sensor on the environment between 8 and 17 grams per kilogram in salinity. So nodes data are logged were logged with hyperterminal. So we acquired 1 point nodes for 22 points of SB9 measurement. That's why it looks like some profiles. So on the blue line, we have the salinity nodes between 0 and 30 met of depth. And the black line is the reference salinity. So and the same. So we have the profiling temperature below for 3 example of profile. So we have a good behavior and very good shape and between the node salinity and the reference salinity. We observe some problem of correction lag and some problem of response time of the node sensor due to the low frequency of measurement. So I represent other campaign with the node sensor in the North Sea, but the difference we achieved 100 profiles with the node sensor up to 700 met depth in an environment between 29 to 35 grams per kilogram in salinity. So the parameterization of the nodes was the same. So I plot some some example of station. So we have a good behavior between the nodes and reference salinity in temperature 2. So if we zoom on the screen on the graph, we measure difference of salinity. So our hypothesis is due to disalignment in temperature. So we need to correct this default. So if we check the temperature profile, so we have the disalignment in temperature. Another station example. So with the node sensor compared to the practical salinity of SB9 and reference salinity SB9. So we have a very good behavior. Another station here. So we have very good profile. Another station, GN014. So as we can say on this cruises, so we have a very good acquisition of data. We have very good transmission. We have very good architecture, plug and play for CTD carousel integration. So the 2 points that we identified is that we highlight low response time of the node sensor on this type of platform. So we need to increase the sampling frequency of measurement of the node sensor. And another point that we identify is the power on time for node sensor before launching its acquisition. And we need also to correct the channel lag of node sensor because on ascent and descent, the speed of CTD carousel is 1 meters per second, and it's 10 times greater than float speed. So to conclude, the new crisis will be reported in 2021 due to COVID-19 crisis. So we will expect new profile of absolute salinity next month in the Mediterranean Sea. And during this crisis, we assess a new version of node sensor optimized with new correction of ambient light, new mechanical design, and optimize, of course, we will optimize the float mission. So just my last sentence is, so Enki is opening up to new opportunity of cruises in open ocean to target deployment in the water, such as Indian and Pacific Ocean, but because we know that on this area we have very high composition anomalies. So where seawater salinity anomalies are more likely to be present, of course. So thank you for your attention. And if you have some question, I will respond after.
Thank you very much, Damien. That's a really interesting talk and fascinating to see. So I'll just ask to see if there's any questions from the floor. Eduardo, Pierre.
So yeah, I have a number of questions, but I wonder if we want to ask them now or at the end.
Well, if there's one now, I think, and then we'll save the rest for the end.
If that's okay. Okay. On slide 23, I was curious about the salinity offset between the NOS sensor and the Seabird, because it shows like it's offset throughout, and I wondered if you had anything to say about that.
23. Sorry, just check here. Okay. Can you repeat your question?
Well, just curious about what do you attribute the salinity offset between the NOS and the Seabird?
At this time, it's just difficult to respond because we during this crisis, our colleague realized some sampling. So they analyzed in they will analyze this sampling these samples in laboratory to estimate if we have a really composition anomalies.
Okay, great. Thank you.
Okay, right. Well, we'll save other questions to the end. Thank you very much for that. So I'm going to move now to Eduardo Vaz from RBR, who's going to talk about the application of the new RBR CTD on gliders, I believe. So really interested to hear that. So thank you very much, Eduardo.
Okay, I will share my screen. Thank you, Matt. And thank you, everyone. It's a pleasure to be here at Oceanology International. And I wanted to spend some time talking today about the RBR Legato CTD that we have developed for ocean gliders. First of all, let me backtrack a bit and just tell you a bit about RBR. If you don't know, we have been around for about 45 years. The company is based in Canada, and we have offices throughout Canada, as well as in China, in the US, in Australia, and in France. And this allows us to really be in time zones that serve our customers. Beyond that, we have a global network of expert agents and resellers that we work very closely with, and we train as well. So our goal is really to be as timely in responding to support and inquiries from our customers. Our goal as a company, oh, sorry, for some reason this is in some sort of schedule. So I'm going to backtrack a little bit here. Our goal as a company is really to develop high precision research grade oceanographic instrumentations that have the lowest power consumption and the highest accuracy as possible. And we have been successful in doing this for many decades. And because of this, our instruments have been deployed throughout all oceans. And this has given RBR a global oceanographic acceptance. Our instruments have WOSI level accuracy, so at the standard of the World Ocean Circulation Experiment accuracy. Sorry, it's still moving on a schedule, which I'm not sure why, so I need to perhaps speak faster. And again, they're being used by every major oceanographic research center in the planet. So it's, in this case, you see an image here of the British Antarctic Survey, who has deployed our CTDs in the Antarctic on a 5-year deployment in 700 meters of ice and then water at the bottom, using our inductive mooring line mode and telemetry system as well. So in terms of what we produce, before I go into the actual legato, our core is developing sensors. The primary one is a CTD, and as well as optodes. We also have developed loggers, autonomous loggers that carry all of our sensors, as well as third-party sensors, and as well as high accuracy quartz-based pressure sensors. We also have our sensors integrated into systems such as the Wirewalker from Del Mar Oceanographic and the SOFAR buoy, smart buoy systems. And then we have a line of OEM sensors, which is what I'm going to be talking about today. The main sensor I wanted to talk about is the RBR CTD. This is our iconic, now the iconic red CTD, and this is conductivity, temperature, and depth, but the combined one here, that red one that you see, is conductivity and temperature. And this has, again, this high accuracy conductivity. It's around 0.003 millisiemens per centimeter. That translates to around 3 millipsu, and it compares equally to the Seabird pump CTD. Same thing for temperature. It has an accuracy of 0.002 degrees Celsius, same as the Seabird pumped. The depth accuracy is 0.05% of full scale, which is about double the improvement, or twice as good, I suppose, as the pump CTD. And where it shines really is in the power requirement, or the amount of energy it uses. And as an example, at 1 hertz, it only uses 18 millijoules, and that's about an order of magnitude less power draw than the pumped CTD. And we'll talk about the benefits of that as I move on. So the actual inductive conductivity cell, what are the benefits of this? I think as Damien was speaking, and people are very familiar with the electrode-based conductivity sensors, the inductive one can be built with very low aspect ratios. That means that it can be designed to really integrate into the platform, and especially profiling platforms, it can reduce the drag tremendously. it can be built in such a way, and we have built it in such a way that it flushes naturally. That means that the volume and the rate of flow inside the conductivity cell is the same as what it is in the outside. So it's naturally flushed. That means that it does not require a pump. And that means then that it's very low power consumption because there is no pump to be powering. And the other consequence is that it's quiet. It's very quiet. There's no really noise being generated by these cells. So it can be used quite well for passive acoustic, along passive acoustic measurements. It's very robust. It can withstand very low temperatures. It can be frozen and thawed without affecting the accuracy. There's no glass that could crack or anything like that. So it's really an outstanding type of sensor. And it also can measure accurately all the way up to about 10 centimeters from the surface of the water, and it can come out of the water. Of course, it's an inductive cell, so it really is producing an electric field around the conductivity cell or the inductive cell. Therefore, it does need the water for that conduit to occur, but there's no damage to the cell to happen if it's operational and it comes out of the water. It just accuracy is retained up to about 10 centimeters from the air-sea interface. And again, being contactless, not having metal electrodes, means that it's not affected by coating of surface oils. And we have seen in some deployments that there have been surface oils, even down to the top 5 meters in the water column, that were affecting electrode-based conductivity cells by just a very thin coat. And the coating, that kind of very thin coat on the inductive cell does not affect the accuracy. There we go. So now, how do we translate the benefits of these CTD into the OEM world, especially the floats and the gliders? Well, we have created the RBR Argo CTD, and that has been implemented into a number of Argo floats, as well as now the RBR Legato, which is the point of this presentation, which is really designed specifically for gliders and AUVs. The benefits are the low power electronics, very high accuracy. They act as a sensor hub for other sensors as well, and it's very well integrated into the platforms. So let me quickly just talk about the evolution into the Legato by first talking about the Argo. So we developed the CTD to really fit into a number of Argo platforms, and now it's out being used throughout the world in some of these different Argo ones, like the Teledyne Apex, the MRVs, the NKEs as well, and OTC in China, as well as a few others. And what has been what the customers have seen as a value to the Argo program has been, again, the low power electronics means increased vertical resolution, increased deployment duration, and a significant reduction in the cost per profile. And that this has been, it's been quite important to our customers. Again, with no pump required and the natural flushing, then they can do salinity all the way to the surface. There's no need to turn off a pump as it reaches the surface. There's no need to change anything. It just measures all the way to the surface. And again, enabling passive acoustics. It has very high sensor stability, so the time series is well trusted. And again, just having these efficiently integrated sensors into the platform means it's a lot of control in the sampling, and it's all in one data stream. And that has been a benefit for our customers. Now, we have taken that type of value from the Argo program and translated that to the glider program. And that has resulted in the RBR Legato. And it really is, it's not a new CTD, it's an evolution of our existing CTD technology that's well proven and trusted. and into a new form factor that's smooth, that is connected, and has been carefully integrated into the geometry of the gliders to maximize their performance. So the RBR Legato CTD has two flavors, if you will. It has the dry bay. It has a dry bay version. It has a wet bay version. The beauty of the wet bay version is it really allows for the user to replace the sensors themselves. They don't have to take the sensor out or take the glider and send it to the OEM glider manufacturer for the sensor to be taken out and sent to us. They can get a pre-calibrated replacement legato and just swap it in if it's a wet bay. For the dry bay, it really is a drop-in replacement for the GPCTD. So it's the same form factor, the same placing for the bolts and everything. And so it is, it really, again, the aim of this program for the legato was to create something that was as user-friendly as possible. So it's, in terms of specifications, it has a depth rating of 1,000 meters. There's an ongoing work to increase that depth rating, and that's happening at this time. It has a standard 2 Hertz sampling rate and can go up to 16 Hertz, and it has a 100 millisecond response thermistor. And again, that is ideal for these type of profiling applications. Again, no pump, so it has a very low power consumption at 1 Hertz, for example, and same accuracy as your GPCTDs or the standard known GPCTDs that have been used in the past. And the interesting thing is we do change the geometry. So the top, that curvature on the top has been changed to meet the geometry of each specific glider. And they're calibrated based on the body of the glider itself as well. So the certain opportunities, again, as mentioned, silent operation, the passive acoustics, and also improved turbulence studies. And I mentioned already the sensor hub as allowing management into just a single data stream. Again, I think same benefit that we found for the Argo program, extended missions. You can sample both on descent and ascent. You can, because of the placing of the thermistor so close to the inductive cell, it's co-located. That means that we reduce significantly the salinity spiking that occurs due to thermal lag. And we also have a number of free tools available, like the RSK tools that do alignment of C and T, so that we kind of reduce any kind of offsets or manufactured kind of data variations there. Again, the benefit, one of the benefits customers are seeing is this user removable capability on the wet bay. Again, it's wet pluggable, and we offer a quick calibration of 4 weeks, so you can have a turnaround of just over a month from the glider being off the water for calibration. If you have a pre-calibrated legato, then you can do that yourself. In terms of the platforms where the legato has been integrated, we have it on the Teledyne Slocum, both the G2 dry bay and the G3 wet bay, and that it has been deployed numerous times. I believe one of the last ones was from Rutgers University just last month, and there's some really beautiful data coming out from there. We also have it in the Kongsberg Sea Glider or Hydroid or University of Washington. I'm not sure really where Sea Glider lives anymore, but I think let's say it's Kongsberg. And we have here a beautiful image from the University of Washington Applied Physics Lab from Luke Reville and Jeff Schilling. And this was, I think it's in this southeast, I'm not totally sure what this was, but there were some great profiles that came from those deployments. Interestingly enough, in this case, with the sea glider, it's not just the top curvature, but it's kind of the longitudinal curvature as well to really meet the shape of the body of the glider. Again, the goal here is to reduce drag and just maximize the performance efficiency of the glider. Again, it has been integrated into the Alsomar Sea Explorer, both in the kind of as a little backpack when you have hydrophones mounted in the bow section, as well as right on the nose. And in this case, you see it mounted with also with an optode. I believe that is the RBR Coda TODO. And it has been deployed, by a number of teams already on the Sea Explorer as well. There we go. There are a couple gliders in China as well, such as the AMT. And again, here you see that it has been deployed, or it's been deployed with the TODO oxygen sensor. It also has been integrated into a number of the AUVs, such as the RTC's NemoSense. This was just in the last few months. There are the Riptide and the Teledyne Gavia as well. And I wanted to now quickly talk about the flow analysis, how it's we have done a lot of computational fluid dynamics studies to make sure that really this natural flow is as effective as we think it is, and it is, and how it does reduce the salinity spiking and reduces drag. And we have done a number of tests as well at the Hui double diffusive tank, again, a Woods Hole, Ray Schmidt's double diffusive tank there. And you can see there is a pretty strong gradient at about 3 meters depth for both temperature and salinity. And we have done that this study on a number of units at different speeds. And on the left-hand side, you can see that by doing some of these lag corrections that we do, it brings the corrected measurement very close to the reference measurement. And on the right-hand side, you see that even at very slow speeds, there's an order of magnitude in speeds here from 98 centimeters per second to 9.8 centimeters per second, that the conductivity remains, the precision remains pretty good. And so these have been very good results that again highlight the natural flushing of this type of conductivity cell, even at lower speeds. Let's move on. So this is some data from the University of South Florida. This was done in the Gulf of Mexico, and this was a legato being deployed. And at the same time, a CTD was casted. It was a concerto CTD, I believe, from the ship. And it just shows, how close these two were. We're just down to about 35 meters. And there's a bit of movement there in the salinity of the ship cast, and it's hard to tell what was happening there or what was going on at that level. But you can see that the legato is remains fairly stable. There is a correction in the data now. That's spiking there. There was a lag in the temp and in the thermal mass there, and that was corrected using our free MATLAB RSK tools processes, so that just in post-production it was able to correct some of those spikes there from the raw, which is a blue in the center, to the red, which is a corrected one. So that was very good data that we got from University of South Florida. This is some beautiful profiles of this sea glider from University of Washington all the way in Guam, all the way down to 1,000 meters. And this was for temperature and salinity. And quickly, I wanted just to close by talking about the sensor hub integration. Again, it allows for multiple sensors to go into the legato, such as the TODO or our quota temperature. And here it's being seen on a slocum where it was used to actually get ambient temperature above the surface. And the TODO was used on the Petrel glider to go to 1,000 meters in China, and gave at 1 second oxygen sampling rate, it gave some really beautiful contours of oxygen all the way down to the bottom. So again, just to close, we believe the Legato enables for more autonomous platforms, better data, longer missions, more sensors, and more collaborations with OEM manufacturers. So with that, I wanted to say thank you, and I'm open to questions now.
Thank you very much, Eduardo. That was great. So I'll open up for one question, and then we'll have a longer discussion session at the end. But Damien, here, any questions for Eduardo?
I have a very quick one. What is the deployment durations that you have achieved? What is the longest deployment you had your CTD on for?
On a glider?
Yes, or yeah.
I'm not sure if I have an actual number. I know that there have been a couple that have been on the water for months, and so 3 months at least. But again, it depends on what other sensors they have and what the capacity in the glider itself is. So let's say that the Legato is the least of the power concerns on the deployments generally.
And just a comment on the Sea Glider, of course. So the Sea Glider is indeed with Hydroid, and Hydroid is not with Kongsberg anymore. Hydroid is now part of Huntington Ingalls.
Right, right. Yeah, I remember that was, I'm not sure when the transition actually happened. So thanks for that correction there, Pierre.
No problem.
Okay, great. Well, look, I'm looking forward to the discussion that's going to come at the end of Pierre's talk. So next up is Pierre Fitzig from Kongsberg Maritime, and he's going to talk about active acoustic sensors.
All right, so thank you very much for the introduction. Great to join this session, which actually is a nice composition, isn't it? We've got an optical sensor starting, we got a conductivity-based sensor on second, and now here the third presentation on acoustics. So as you can read, active acoustic sensors for gas bubble detection. There is a lot of developments happening in the acoustic environment, and acoustic sensors are used to measure quantitatively and qualitatively more and more different targets in the water column. While this is going towards very small targets, such as even plankton, this presentation now aims at targets which are fairly straightforward and fairly easy to detect with acoustics, namely gas bubbles. So let's get started. The work that you'll see on the following slide stemmed from investigations that were conducted as part of a project called ACT for Storage, Acoustic and Chemical Technologies for Environmental Monitoring of Geological Carbon Storage. And this project aimed at better understanding the capabilities and limitations of acoustic and chemical technologies for application in the context of carbon capture and storage monitoring. As you have seen from the introduction slide, this talk now will not deal with chemical technologies. It will just focus on some of the results obtained with the acoustic technologies. The project lasted from 2018 until 2020. And it was under the project lead of NGI, namely Anne Elizabeth. We had many different Norwegian partners, NIVA, NURS, FFI, and the University of Oslo, and the University of Bergen, and we had industry involvement from the companies you see here to the right. Funding came from GasNova and the industry partners. Little introduction on geological carbon storage. GCS ITMS is a promising technology towards reducing the greenhouse gas emissions and to meet the international climate goals. It is applied actively, for example, in the Sleipner field, and also the Northern Lights project could be an interesting search if you are interested in this field. If you conduct GCS or CCS, you have to ensure that the reservoir is properly sealed and that your CO2 is not leaking into the environment anymore. And single and multi-beam echo sounders are promising and powerful technologies in order to map and monitor these sites. The content of this presentation has also been published in an article given in C Technology. You can follow this link later on. And there is also a very interesting presentation given by Scott Loranger on this topic and even further reaching topic. So, as part of the project, different in situ experiments were conducted. In 2019, in the Oslo Fjord near Horten, over here and on this aerial picture, a range of acoustic instruments were deployed, both from a vessel passing over the gas release as well as from a seabed template. This slide gives a little bit more details on how the site looked like. So 100 meters from shore and 64 meters apart, two different locations for installations on the seafloor were identified. We had an acoustic sensor template with acoustic sensors insonifying the area of the gas release. And the gas release had a leak template at 60-meter water depth, where CO2 and air releases took place from release rates ranging from 0.13 to 35 liters per minute. And there was this additional template with chemical sensors that was in the vicinity to the gas bubbles. This slide gives a little introduction to different acoustic techniques. So as you can imagine, you have many different options and opportunities to get sound into the water. And with the different options, you have different properties. Let's start with a single beam configuration. So a single beam configuration is a vertical beam, usually a vertical beam pointing downwards. It's a classical quantitative echo sounder. If you have split beam technology here indicated by these small lines, you basically split the beam into some sections, and the sound coming back is recorded by these different sections, and this helps you identifying and positioning targets in your beam, which is very powerful if it comes to corrections related to distance between transducer and your targets. The narrow beam also helps with a good resolution, and these instruments got fairly small, such that you can install them on various platforms these days. You use these type of single beam echo sounders both for water column as well as seabed measurements. A multi-beam instrument can be understood as many single beam instruments next to each other. So you have a fan of individual beams. These can either be in the form of a swath, or they can also be arranged in the form of a matrix. You, by that, have the advantage of insonifying a very large volume. So you can either investigate a large water body volume, or you have a large area coverage on the seafloor. You can use such a system for bathymetric measurements, but you can also use it for water column investigations. Finally, and third in the row, are sonars. Sonars are referred to as omnidirectional systems. So you can look into almost all directions, starting almost immediately under the water surface. So this is very powerful if it comes to mapping fish schools, and you typically use a sonar for water column targets. This slide now gives an overview over different instruments that were used in the study. So let's start off with the EK80, being a science, being an echo sounder usually applied in ocean science. It's a single beam instrument. You can get it on almost all platforms if size and power consumption allows. But if it comes to the EK80, it's a fairly versatile unit. You have various frequencies that you can get transducers for. These transducers and frequencies are then either run in continuous wave mode, which means you are operating at a distinct frequency, or you can go into a frequency modulation setup where your transducer is running, sweeping through different frequencies, which goes in line with some advantages. You can deploy these units down to very high water depth. You have fairly narrow opening angles, and you have a fairly large range, and you also have a fairly large depth rating. The next in line is a multi-beam M3 inspection inspection device. You have a higher frequency, a lower range, a fairly large opening angle, and a high depth rating. This is basically for acoustic imaging. The EM2040 is a multi-beam system, a compact multi-beam system, usually used for bottom metering, but allows also for water column measurements. You can achieve realized measurements from 200 to 400 kilohertz at a 600-meter range. It also has a high depth rating to be installed on ROVs, for example. And the opening angle is also extremely wide, such that you can cover a large area. The SN90 is a combined sonar and single beam device, usually used for fisheries. That's why you typically install it on vessels. The range is 900 meters and the depth rating is 20 meters because it's on a vessel. The ME70 is a powerful combination of single beam, calibrated single beam devices and multi-beam capabilities. You have a maximum range of 900 meters and a variable opening angle, and it's again a vessel system. And finally, an EM712. It's a bottom mapping system, a multi-beam system with a large range. So it's basically usually a bathymetric system for a vessel. With these small items, you will see which sensors were installed on which platform for the studies I am going to show you. Let's start off with the acoustic template. So the acoustic template, installed several 10 meters away from the gas release, was comprised of the lender structure with a pen and tilt unit. And on this pen and tilt unit, you had this acoustic imaging multi-beam sonar, as well as a single beam echo sounder with two frequencies, namely 333 kilohertz and a 70 kilohertz. And as you can see from this schematic here, these transducers were basically horizontally pointing towards the gas seep. Also indicated that the imaging sonar had a very large opening angle, and the quantitative echo sounder was narrower in order to realize for better quantitative measurements. The echo sounder itself came in the form of a WBT tube, to which then the transducers were connected. The next in line on the lender, we have the M3, as mentioned. It is a 500 kilohertz, 140 degree opening angle imaging sonar, and it provides you a very good overview of the structure and the gas leak. So what we see here is a direct image, so no post-processing is applied. And here to the right, we have zoomed into this section, and what we see here is the leak template with a gas plume and the chemical sensor template behind it. So it provides you a good overview of the environment. Here we see data from the EK80, the quantitative single beam device. This is data from 1.3 liter per minute CO2 gas release. It's basically the stationarily deployed EK80 on the lender pointing towards the plume. And we see that over the time, the distance between the transducers and the beam varied due to currents based on the fluctuations of the plume within the water column. So, and it is also extremely sensitive, so gas releases down to 0.13 liters per minute could be detected. The advantages of a calibrated acoustic device in such a context are that you can locate the plume in terms of range between transducer and the plume itself. You can detect the density of the plume. You can investigate the dispersion of the plume width. You can also derive the target strength and the mean target strength and the total target strength. And you can also estimate the amount of gas that has been released. Let's now swap to the vessel. The vessel used is the Simrad Echo, It's based in Horten, where our main sensors and robotics facilities are from Kongsberg Maritime in Norway, and it is equipped with a large suite of acoustic instruments, such as the ones that we have discussed earlier in the table, and you are going to see data from now. So let's look at how the EK80 data looks like from the vessel deployment. So here we see the surface of the water going down with depth, down to the 60 meters where the gas release is, and we see the signal from passing over the plume at various frequencies, 18, 38, 70, 120, and 200 kilohertz. So we see that in all cases, a rising height of around 40 meters could be observed. We also see some distinct features in the surface of these echograms. They result from a layering in the fjord environment. And it's also important to mention that with only 7 degrees of an opening angle, you have to be spot on your gas release plume. Otherwise, it's difficult to see it. This is something we will encounter going forward now. As I mentioned, the EK80 is a quantitative instrument, so it is calibrated, and that helps you to basically add a number to your gas plume. So you have a feeling for the target strength of the individual targets that you see in your echogram, and also for the overall backscatter scattering efficient. You do not only see these direct numbers, but you also have target strength distributions and mean values. And this can help you if you want to correlate your results with bubble size distributions or in general gas release rates. Here to the right, we see how this split beam capability looks like. So in this example here, we see that the bubbles could be detected in this sector of the beam, which again helps you if it comes to target signal correction along the range of the beam. Let's jump on now to the multi-beam system, the EM2040. As I mentioned, it has a fairly wide swath opening, and this shallow water multi-beam system is usually used for bathymetry, but still bubbles in the water column represent very strong reflectors, and so you can also see them nicely in the water column information from this device. And the rise height is comparable to the results obtained with the EK80 measurements before. Now we move on to the fisheries sonar, to the SN90, and again we look at the images obtained with 1.3 liters per minute from the CO2 plume. And here the device was configured that we had 5 beams, here indicated in gray, 3, 4, 5. And as you can see, these beams point in different directions, and this is the explanation why you see the beam or different sections of the beam, of the plume, sorry, in beam 1, in beam 2, and in beam 3, while you only touch some parts of it in the other beams. So this beam, actually, the inspection beam number 2, showed the highest rise height up to 50 meters and only 10 meters below the water surface. The ME70, as mentioned before, is a powerful device that combines the coverage advantage of a multi-beam with the ability for quantitative measurements. You can configure up to 45 beams, and in this case, only 5 beams were shown. And here in the center, they were all put together to form this acoustic image of the beam, which is not different from the other ones we have seen, but just to give you an impression of how measurements of this device look like. And finally, we conclude with a stacked image obtained with the EM712, which is, as mentioned before, a deeper water system usually used for bathymetric measurements. And we basically have a stacked view here. So every small line that you see is one measurement, and the vessel has moved over the plume. We see here the plume as well as some other features in the water column, and again, surface and the bottom at 60 meters. This was an image recorded with 1.3 liters per minute of CO2 gas release. And this one has been recorded with the same volumetric flow rate, but not with CO2, but with an air plume instead. So it was experiments were conducted with the air plume as well as with the CO2 plume, because as you can see, there is a much stronger reflection coming from the air plume. And this results from the lower solubility air has compared to CO2. So that's why the rise height of this plume is higher, and the general intensity of the signal is much more distinct. Data from these acoustic sensors can be viewed in real time in 3D in a software solution called TD50 that can visualize the data from different acoustic instruments. And here we have just picked out two. To the right, we see the ME70 multi-beam system. And here on the lower left, we have two images of a single beam device. In the single beam device, you see the limited 3D capability, because it's basically just a single beam with a 7-degree opening, whereas here to the right we really see a 3D image of the gas release, of the CO2 gas release, and actually we have also passed over a fish school here in the beginning. So this brings us to the conclusion. So shape, intensity, and the spatial development of gas plumes were clearly detectable with all different types of acoustic instruments. All these instruments observed CO2 bubble rising heights of around 35 to 40 meters above the release point. And of course, what you see from the plume depends on the geometry of your beams, where you're pointing at, where your vessel is. So that's something you always have to keep in mind when working with acoustics. Active acoustics are a sensitive method for monitoring and quantifying gas leaks from almost any platforms. Here we have shown a seabed template as well as vessel data, but you can also mount them on unmanned or uncrewed surface vehicles, AUVs, or other mobile platforms such as an ROV. There is a large number and variety of acoustic instruments available that can cover various monitoring scenarios, high resolution quantification of individual bubble seeps, up to the mapping of large areas for observing the temporal distribution of gas leaks. And with that, I would like to thank you for your attention, and I'm looking forward to having the discussion now.
But thanks for that. That was really interesting. I mean, really fantastic to see a way of being able to quantify and identify and locate CO2 potential leakage, which I think gives us a lot of hope that we'll be able to manage carbon capture and storage, which is a great thing to see.
Matthew, you get very silent. It's hard to understand you.
Ah, am I still silent?
No, that's better.
Okay, all right. So great work, Peter. Thank you very much. I guess I have a question around your particular location. So the bubbles seem to go up very vertically and quite high in comparison to some other release experiments that I've seen. Was that because there was low current, or was there some other issue with the maybe reduced solubility of the CO2?
It is actually, that's a good question, and there are there were several experiments in this direction going, and there was also an exchange beforehand about planning a proper in situ study, because it's not that easy. And in effect, it's actually, it was the second in situ study during this project, because the first one was conducted within the bay that you saw. So not behind the island, but before the island in the aerial picture. And that led to less useful results. Why? Because there was even less or lower open water flow and even stronger stratification. Whereas in order to use these results for a meaningful data that might be applicable in North Sea environments going forward, they moved outside the bay to have this more North Sea-like environment. Yes, currents were fairly low. You still see, I mean, even here behind me, you see this small curvature. So there is some water column influence, but it is definitely less significant as if you were in a, let's say, tidal influenced central North Sea environment. But you point to a good point here. It's something that always needs to be considered.
I mean, it's really great that the acoustics can pick up that difference, right? So it tells you something about the environment as well as the leak, which is really interesting. I mean, certainly, so I was involved a bit with the STEM CCS project that did a release in the North Sea, and the bubbles went much less high in the water column, much lower. So but the acoustics that you're presenting look like they would have picked that up, and that tells you a lot, I think, which is great.
I think this is the reason why they also came with the air mixture as well, right? They didn't know what to expect beforehand, how high the rise height would be, so they had the air as a good target in their plant. Yeah.
Okay, great. That's fantastic. Thank you all for your talk. So we're going to enter the discussion session now. So just to introduce myself, all the other speakers have spoken. I'm Matt Molam. I'm no longer, but was previously the head of the Ocean Technology and Engineering Group at the National Oceanography Centre in the UK in Southampton. I'm now a principal investigator in the NOC in Southampton, and I'm also director of a new company, Clearwater Sensors. So we're going to have a panel discussion now, questions based on the talks and the collective experience of many years of working in this field between us. And so I'll be happy to take a question for the floor, which can be directed to any of us from anyone. So I know that there were a number of questions from each of the talks. We'll start there, and if not, I can pitch one in.
Yeah, I would start directly for Damian. So you mentioned, or it was very nice to see this sensor in action, both in normal salinity regions, in open ocean regions, but as well as in the brackish environment of the Baltic Sea. Do you expect an equal performance of this type of sensor from a 0 salinity to a 35 range, or do you expect some challenges to occur if you go below these 12 or 14 that you had in the, or what was it, 8 to 14, or if you go below the Baltic Sea conditions? I mean,
for us, we expect to calibrate the NOS sensor, because the first demonstration that I present today is Mediterranean Sea, so we have a salinity approximate across 38 gram per kilogram. So of course, it depends on the sea. We can calibrate the NOS sensor between 0 and 12, maybe until 40, because the algorithm that we implement is available for this range of salinity. So it's not a problem. We expect. That's why we need more data, we need more environment, because to discover some new environment, of course, and the result that I present in Baltic Sea is very interesting, because we measure between 8 and 17 grams per kilogram. So it's the first time that we evaluate on this kind of area.
Really interesting. If I can pitch a question for you as well, please, Damien. So you present the uncertainty of the refractive index measurement as about 10 to the minus 16, which is pretty good for a prism. Do you see any, so that uncertainty, how much of that is built up of a precision measurement, and what's the sort of long-term drift or change in that over time? Have you done some long-term tests in, say, a known calibrant?
Yeah. For a long time, we don't have enough data after 4 months with the NOS sensor, so to estimate the drift on the float on the sensor, it can be hard. We need more experiment to evaluate a long deployment and to evaluate this drift.
Okay, well, it looks really promising. Thank you.
Yeah.
I've got another one. So something that's very interesting for me, not working in the field of CTT sensors, is to understand now where you see the niche or the market for the optical sensor and where the traditional conductivity cell units will have their place. So, I mean, we heard very interesting numbers from both of you, but it would be very good to hear where you see the advantages for both of the technologies, and why would one be used in one region and the other one in another.
And I just specify for the no sensor, it's an optical sensor. So in fact, we measure non-ionic component in the water versus conductivity sensor. Of course, we measure only ionic parts of the dissolved material. So with the no sensor, I missed during my presentation, but we measure exactly all dissolved material in the volume of water. That's why we have some difference. Sometimes it's difficult to determine. That's why we need some sample in laboratory, and we need some sampling analyzed in laboratory with densitometer, of course, to evaluate the anomaly composition anomalies. So that's why it's very, very difficult that you have a new sensor measure a parameter completely different with practical salinity that we met on the ocean. So it's very hard sometimes to just why we have a difference. Why is due? For example, it's the problem of time response time. It's just we observe salinity spiking. Why? So it's hard. I think that is hard after a few words. Few years, it's very hard to play very good result and respond to everyone that why we have a difference.
I think from my side, Pierre, I think that obviously the electrode and the optical and the inductive technologies all have their place. I think the one thing that and I think I probably mentioned it one too many times, is in the case of inductive, low power is one of the big kind of capabilities or values that we provide. So applications where you are very power constrained, when your payload is drawing already enough, and you need to go for long missions, then that's where I see inductive being useful. I think optical can be fantastic. I mean, it can be very fast as well if you need to. But there's the complication with optical. I think in all situations is just a power draw on any optical and any optode. So it's maybe long-term deployments would not be ideal for an optical type of sensor.
Well, I think we should give Damien a little break. So I'm going to ask you a question, Eduardo.
Sure.
So you talked a bit about the surface layer of oil problem. So presumably even an inductive cell will get a coating of oil, and there'll be a physical geometry effect of a insulator coating inside the inductive loop. But I guess, talk me through the geometry. Is the layer just so thin that it's insignificant in comparison to the measurement you're making?
That's correct. I mean, if you look at the volume of water that we're measuring overall, it's around 15 centimeters surrounding the cell. About 80% of that measurement really is happening at the center. Just if you look at the field lines, the way that the electric field lines would be. But yes, I mean, the test that we have done is the oil coatings will be so thin to be really just unperceivable in terms of the accuracy. Of course, as if you have a barnacle stuck inside, then that will be noticeable. Or if you have a lot of fouling on the surrounding area, that will be. But just the oil is not a concern for us. And I think with electrodes, what you do see is you just need even a minimal layer of oil is enough to just break that conduction channel.
It certainly have to be managed in conducting electrodes. I mean, there are ways in which that oil can be removed, but or worked around. But yes, it can be problematic. Interesting, really good. And you presented some really nice metrology or specifications, at least in terms of, you know, this looks really very good in terms of getting very high accuracy, salinity, temperature, conductivity. Did you, I presume you had to, like the rest of us who've tried, had to work on drift within some of the sensors, perhaps with the temperature sensor. How have you built up your confidence in your uncertainty measurements and your drift corrections or knowledge of drift in some of the core sensors?
Yeah, I mean, we have, you know, the stability, for example, in conductivity is about 0.01 millisiemens per centimeter per year. And in temperature, I think I remember it being 0.002 degrees per year. So it's, you know, they're, I would say, all things considered, they're fairly low drift. Again, depends on the situation, but we recommend them being calibrated once a year, and that generally keeps them within the spec.
I guess my question was how you can be sure that that's, because that's very good, right? And once your sensors become that good, it actually becomes quite hard to be certain that that is actually what the drift is, because, you know, there's noise sources in other areas and you actually need quite long data sets. So have you got long data sets that you, or a number of sensors that you can build up the certainty in your metrology or your stated specs?
Yes, I mean, I would say we have an expert in you know, and the actual calibration and the drift. Actually, we have, you know, a couple of them, but we have in the lab, I know that we just keep from just real samples and just using the salinometers and just keeping those for long terms to see what the drift is. You know, in terms of doing kind of field samples, that, I mean, that has been done again by our customers. I'm not sure if I could point to data sets in the field that we have access to show that, but I think, you know, it's in general, the customers have shown that using bottle samples, the drift has been quite low.
Yeah, that's great. I mean, it's great that you're deploying on floats and gliders, right? So you're going to get more and more data, and the more that gets intercompared, and you get climatology, and you get you know, things like Go Ship reference measurements nearby the instrument, the more data that the community is going to have to.
That's right. Yeah, yeah.
It's great. I'll pause for questions because I've just asked a bunch.
Okay.
Okay, got another one. So, Eduardo, how easy is it to clean such a conductivity cell? I mean, we spoke about this oil film, then you mentioned the fouling and the potential barnacle. I mean, can I just take a brush and give it a nice clean, or how sensitive is the device?
It's not that sensitive. Well, the word I don't think is sensitive. How fragile it is. It's not fragile. It is. It's easy to just use a cloth if you want, or a soft brush in the inside, and that's generally what people do. If there's no visible fouling, then generally you don't have much effect on the accuracy. It's you know, we are working on anti-fouling technology for that type of sensor, and we're hoping to release that in January. We're hoping to release it in the fall, but, you know, there were some global complications, so I think hopefully we have that out, but even once you see the fouling, it's fairly easy to just wipe it off. But yes, that is one of the elements on, I would say, any sensor that when you are looking for this level of accuracy and your tolerance is very small for any changes in that accuracy, then you have to have a plan for maintenance and cleaning that it's in some locations even every few weeks. Yeah, so it depends on the application.
Okay, Pierre, I have one for you. So, so the acoustics really make the bubbles stand out in the data really clearly. It looks quite a good way to survey large areas and search for bubbles. So have you tried a number of different techniques? I mean, thinking about a operational offshore gas reservoir, or I guess even pipeline leak detection, what would be your recommendation to people doing operations in terms of which systems to select and how to use them for the most cost efficient and therefore probably carbon into the atmosphere efficient use of the technology?
Yeah, I mean, you just mentioned the magic word there, which is cost efficient, because I think all the technologies for safe monitoring of CCS sites are there. It's just about a cost efficient and a very effective way of having a good monitoring at a high certainty. So I think going forward, you could go, depending on water depth, where the site is, but let's assume North Sea environment. I think that an uncrewed surface vehicle with a bathymetric multi-beam system is fairly powerful because you have an extremely large swath area. You could use that for general mapping of the area. Then you could have the same vessel equipped with a quantitative narrow beam echo sounder as well. So in case you see anything reflecting in your big swath, you can still go there and take a quantitative measurement from your center. And then I think this is hard to beat in terms of efficiency and also cost effectiveness, because you can run the surface vehicles for an extremely long time. If you have more funds available and you can still good, if not even better, resolution data from AUVs. You could use acoustic systems on AUVs, which also have extremely large opening angles, and you would also cover extremely large areas. Of course, your deployment duration is shorter. You might have a few days instead of a few weeks that you can achieve with the unmanned surface vehicle. And then if you are aware of critical areas, such as you might know about fractures, or you know about certain, let's say, welds that have been left or something, you might deploy some point sensors there to really have a good surveillance of a certain spot. So you have to make a proper mixture and keep in mind, as you mentioned before, the current situation and the stratification in the water column, and you must understand the chemistry. So it's a complex situation, but a lot is done in this direction. And let's say in the last years, I had the feeling this topic slowed down a little bit, but it recently picked up again. And looking at the ambitious goals all the nations have, CCS might become all vogue again and again. Technology is there for application as well as for comprehensive monitoring.
Very good, thank you. Okay, so I'm going to pause again. Any more questions from the floor? Okay, so I have a sort of general biofouling question, I guess, for the non-acoustic sensors, which tend to be more prone to it. So you talked about a strategy that's coming, but Damien, is anything on that sensor currently managed in terms of biofouling? And do you think future plans are going to be affected by regulations? I mean, some of the current incumbent conductivity and therefore salinity density platforms are using some materials that probably won't be allowed to be used in the future to try and combat biofouling. Perhaps you could talk, perhaps a bit more of a philosophical question. What can we do as instrument manufacturers to stop biofouling without using toxic and potentially banned materials?
So yes, of course, you speak about biofouling in a platform has a profiling float. The problem of biofouling is not very important. I know I say because the float stay only a short time on the surface to because it transmits data, of course, and it stay very short time. So of course the problem of biofouling is not very important on this kind of platform. So maybe after few years, I don't know, I can estimate this part. So but we have also think about or engage a reflection on the development of biofouling resistance on the NOS platform, on the NOS sensor. So I can't tell you how kind of technology we have decided for the NOS sensor, but it's in development at this time at InKey instrumentation.
Yeah, very good.
Because you have a lot of, sorry, yes, it's all right.
Sorry, Eduardo, how your approach to biofouling without using toxic materials?
Sorry, Matt, you're cutting off a bit. Your audio just comes in and out. Sorry.
Sorry, I'll try leaning forward, and it might be a compressor issue. Okay. So, Eduardo, perhaps you could outline your thoughts around using toxic materials or not in biofouling prevention.
Yeah. Well, I mean, I think we see the writing in the wall. I mean, using TBT is not a good idea, and it is being banned throughout. The fact that it has been grandfathered in many programs, I know in the UK as well, in some places, it's one thing, but that I don't foresee that will go on for too much longer. So, yeah, we're taking a non-chemical based approach. You know, I suppose I can. You know, by the time this is released, we'll be really close to being, you know, able to release. So our technology will be based on UV light. So I think it's clear this is where things are going. There are other manufacturers working on this. I think we have a very novel design that allows this to happen, and it has been in tests in the field throughout the summer, and it has been extremely good performance. And I think the first deployment to a customer is happening in Italy in February, which is why it really has to be commercially released in January. So that's kind of our push. But we have a lineup of kind of early customers for this, and it will be really interesting to see how it works in many different environments. But yeah, and again, there are other developers. It's not, you know, many papers that have been published on UV, and it's you know, one of the clear approaches that will be long term. The one thing is UV being again just optical, or it has a power draw element. But I think it's fine. It fits in some situations, the more situations where we can maybe get a bit larger battery canisters, and you know that can be mitigated. In the areas where, kind of as Damien mentioned, profiling gliders and floats where fouling is maybe less of a concern, then you know, we have the power balance there is fine.
Yeah, so presumably you can use less often and less long duration UV exposure in the lower fouling environments, which may actually be fortuitous, right?
Yes,
Argo
exactly.
is very low power. Okay, that's brilliant. Thank you very much. Any more questions for each other? Okay, well, look, I think we've really explored some of the common problems and in details of each of our technologies. Thank you very much, everybody, for your talks. They were all great, and thank you for participating in the question and answer session. So that ends the ocean observation track on the effective use of sensors, and thank you all very much for your time.